Hello, everyone. So last time we finished chapter 2 and the topic of cardinality of sets. And as I said last time, we are going to skip chapter 3 and we'll get started with chapter 4 today, which is about number theory. So as I said in the very first lecture, number theory is normally considered as a separate branch of mathematics and not a part of discrete mathematics because it's so vast itself, although it deals with the set of integers, which is a discrete set, but because it's so vast itself, so normally it's considered a separate branch by mathematicians. And of course, it's very much, although it's a separate branch, but it's very much related to many other important branches of mathematics, such as algebra or analysis or discrete mathematics. But now here in this course, we just want to go over some basic concepts of number theory briefly. We don't want to go into much details or much depth. For a deeper understanding of number theory, of course, you can take a third year, for example, undergraduate course in number theory, which is just about number theory. And then, of course, you can take more advanced courses and many graduate level courses we have in number theory in all universities. So let's start with 4.1, which is about divisibility, modular arithmetic, and division algorithm. So we want to start with the definition. Let A and B be integers with A not equal to 0. We say that A divides B and we write A divides B. So when do we say that a number divides another number? A divides B, it's same, it has the meaning that A is a factor of B, or in other words, B is a multiple of A. When do we say this? For example, 3 is a factor of 12. Why do we say that 3 is a factor of 12 or 12 is a multiple of 3? Because there is another number, which is 4 in this case, such that 12 can be written as 3 times 4, right? So in general, we can say A divides B if there is an integer k such that B is equal to k times A, right? For example, in the example I just said, 3 and 12, 3 divides 12 because there is a number 4 in that case, which is where 12 can be written as 3 times 4. So when we write A divides B if there exists an integer k such that B is equal to Ka. In this case, we say that A is a factor of B, or B is a multiple of A. So if A does not divide B, we write A does not divide B. Okay, so as an example, like I said, we can say 3 divides 12 because 12 can be written as 3 times 4, right? So here, k is equal to 4. Or let's say 5 does not divide 12 because there exists no integer k, right? Such that 12 can be written as 5 times k. 5 times an integer is always a multiple of 5, but 5 times an integer k is a multiple of 5, but 12 is not a multiple of 5, so 12 cannot be written as 5k. So there is no k such that 12 is equal to 5k. Okay, so now let's look at some properties. So the first property, if A divides B and A divides C, then A divides B plus C. So let's see how we can prove this. Proof. So A divides B implies that B is equal to KA, right? For some K. And A divides C implies that C is equal to, so let me call this one K1. C is equal to K2A, again for some K2. Right? So please remember that the most important thing when you want to prove a statement is applying the definitions. In this case, we have a definition for A dividing B. What was the definition of A dividing B? We say A divides B if B is equal to KA for some K. Now I have two assumptions here and one goal or conclusion. The first assumption is that A divides B. So how can I write this in a mathematical form? In other words, how can I apply the definition here? I can say that B can be written as, let's say, K1 times A for some integer K1. Say for some integer K1. And similarly, A divides C means C is K2A for some integer K2. Now, these are my assumptions. What do I want to show? I want to show that A divides B plus C. A divides B plus C. So how can I do that? Well, if I look at my assumptions, I have B as K1A, C as K2A. And what do I need? I need B plus C, right? In the conclusion, B plus C is appeared. So I can at least try to make B plus C appear, which is very easy to do, right? Because I have B equals K1A, C equals K2A, and I need B plus C to appear. Well, I can just simply add these two equations. And what do I get? Then I get B plus C equals K1A plus K2A. And that can be written as K1 plus K2 times A. If I take A out, right? And this means that, again, by definition, according to definition, I can say that this implies that A divides B plus C, since K1 plus K2 is an integer. Right? If B plus C can be written as some integer times A, then that means A divides B plus C. And B plus C here is K1 plus K2, which is an integer. Why? Because K1 and K2 were supposed to be integer. Therefore, B plus C is we wrote it as an integer times A, which means A divides B plus C. Okay, now next property. If A divides B, then A divides BC for every integer C. So I think you got the idea for the proof, which is somehow similar to the idea of all the proofs that you have seen, that we have an assumption, we have a conclusion, and we have to go from assumption to conclusion. using the definition. The most important thing is the definition. I repeat over and over because it's very, very important. So what is the assumption here? A divides B. So we know A divides B. So what does that mean? Again, applying the definition means B is equal to, let's say, K1A, again, for some integer K, or some integer K1. Now, but that's all here in this part. I have only one assumption. And now what is my conclusion? To show that A divides BC. Well, I already know B is K1 times A, and I need BC. Now, how can I make, again, so that means I have to make BC appear and then see whether A is a factor of BC or no. Now, B is K1A. So how can I make BC appear? But that's, again, easy to do. I can just multiply both sides by C, right? So then BC is equal to K1 times AC, which is same as K1 times C times A. The multiplication of a few numbers, of course, commutative. I can change the order if I need to do that. So BC, I wrote it as some integer times A. Again, according to the definition, this means that A divides BC. Again, since K1 times C is an integer. Well, that's all. Okay, so proof was simple. You just need to apply the definition properly. Now, the next property, if A divides B and B divides C, then A divides C. So let me leave the proof of this as exercise because we already did two properties, the proof of two properties. So I think you can do this by your own. And the next property, if A divides B and A divides C, then A divides MB plus NC for any integers M and N. Proof of this, again, that we leave as exercise. I can give you an example. Let's say, for example, 5 divides 10, 5 divides 15. So then I can say, so if A divides two numbers, B and C, then it will divide any linear combination of B and C. So this is called BM, MB plus NC is called linear combination. We'll see about linear combination in linear algebra, but for now, the term is not very important. So if A divides two numbers, then A divides any multiple of first number plus any multiple of second number. So now 5 divides 10 and 5 divides 15. So 5 divides any multiple of 10 plus any multiple of 15. So for example, 5 divides 10 times 2 plus 15 times 3. Any multiple of 10 plus any multiple of 15. So i.e. 5 divides 45 plus 20, 65, which is true, right? So this is just an example of this property. Of course, you know that example can never be considered as proof, right? So proof of the property I left as exercise, which is somehow similar to the proof, the two properties that I proved for you. But this is just an example. Of course, not a proof, just an example, just to give you some idea about this property and what it says. All right, so the next thing we want to cover is about division algorithm, which I think you saw in elementary school. And it's very important theorem in mathematics and in number theory. So theorem, let A be an integer and let's say B bigger than 0, be a positive integer. Then there exists numbers Q and R. There exist unique numbers Q and R called the quotient and the remainder such that A is equal to BQ plus R, with R bigger than equal to 0, less than B. So division algorithm says that whenever you have two numbers, so here, by the way, B here, A is called dividend, B is called divisor. So whenever you want to divide one number by another, as long as the divisor is a positive integer, you can do that. And there's always a number called quotient and a number called remainder. And what is the important feature of remainder? Remainder is either 0 or a number which is less than B, less than divisor. And quotient and remainder are always unique. You cannot have more than one quotient, or you cannot have more than one remainder. Okay, so first let's look at an example. Let's say A equals, for example, 21 and B equals 5. What is quotient? And what is the remainder, do you think, in this case? So 21, I can write it as 5 times 4 plus 1, right? So this is, as we said, this is called dividend. This one we said is called divisor. This one quotient. And this one remainder. So here, basically, we can say that quotient Q is 4 and remainder is 1, which is less than the divisor, which is 5, and bigger than equal to 0. Okay, so this is what you learned in elementary school, and you saw some example. This is just a very simple example of division algorithm. Dividend is 21 and divisor is 5. But how can we prove division algorithm? So this is something that you haven't seen in elementary school. So proof of division algorithm. So first of all, the uniqueness has already been proved. Do you remember from previous lectures? The uniqueness was proved. C was proved before. C, May 20 notes. If you look at May 20 lecture notes, and as you know, the lecture notes are on Moodle, right? You'll see that we already proved the uniqueness. So there are two things you have to prove: the existence of such number Q and R called quotient and remainder, such that A is BQ plus R. Remember, what is the goal here? We have two numbers A and B, and we know that B is a positive integer. We want to show that there exist, first of all, there exist two numbers called a quotient and remainder denoted by Q and R, such that A is equal to BQ plus R. And we also want to show that such numbers are unique, so we cannot have more than one Q or more than one R with this property. So the uniqueness has been proved before. Look at May 20 notes. Now it remains to show existence, right? Remains to show existence of such Q and R with A cos BQ plus R and R bigger than or equal to 0, less than B. So to do so, we need a principle, a mathematical principle called well-ordering principle. Well-ordering principle. So what does well-ordering principle say? Okay, so my ultimate goal is to prove existence of Q and R. But to do that, first I need a mathematical principle called well-ordering principle. So well-ordering principle it's a very simple principle and looks obvious, but it has lots of applications. This principle simply states that every non-empty subset of natural numbers has a smallest element. So of course, natural numbers, well, here, remember in this course, the natural numbers, by natural numbers, we mean the set starting from 0, then 1, 2, 3, and so on. So of course, that set has the smallest element, which is 0. And every subset of it, non-empty subset of it, of course, also has smallest element. So every non-empty subset of n equals 0, 1, 2 contains a least element. For example, if I said, for example, A equals 1, 3, 7, it's a non-empty subset of n. And of course, it has the least element. What is the least, or least means smallest? What is the smallest element of this set A? The least element of A is 1, right? So any non-empty subset of n that you consider has always a least element. So this is called well-ordering principle. So you will see also about this principle in analysis course, Math 225. If you take in the very first week, you will see about a well-ordering principle. Okay. Now, how can we prove? So remember, our goal was to prove the existence of numbers Q and R such that A is equal to BQ plus R and R bigger than or equal to 0, less than B. So how can we, so now back to proof of existence of Q and R in division algorithm. So consider the set S defined as follows. Okay, I'm writing the proof for you for existence of Q and R. So S, first we need to define a set S. What is set S? The set of all elements of the form A minus BQ such that Q belongs to Z. Q belongs to Z and A minus BQ bigger than or equal to 0. So set of all elements of the form A minus BQ. Remember, A and B are given, right? A and B are given. We are looking to show existence of Q and R with the properties that we need. Now, this Q is not necessarily the Q that we are looking for. Okay. So maybe to avoid confusion, I can use a different letter if you want. I can say A minus, let's say BM. Okay. Now, A and B are given. We are looking for to find Q and R such that, remember, A is equal to BQ plus R and R bigger than or equal to 0, less than B. Now, I am saying that first consider all elements of the form A minus BM, where M is any integer in Z, and A minus BM is bigger than or equal to 0. Okay, so the claim here is that S is a non-empty subset of N. So of course it's a subset of N because every element of S by definition is bigger than or equal to 0. Is an integer and is bigger than or equal to 0. Of course, every element of S is integer because A and B and M are all integers. And by definition of S, every element of S is non-negative because the definition of S says all elements of the form A minus BM, where A minus BM is bigger than or equal to 0, right? So all elements of S, if S has any element, I'm still not sure whether S has actually any element or no, but if it has any element, it has to be a non-negative integer, and therefore S, of course, is a subset of N. But now the question is, does really S have any element? Because it's still possible that S is empty. So the really important thing to prove here is to show S is non-empty. So to show S is non-empty, so I'm going to consider different cases. So case 1, if A is bigger than or equal to 0, then set M equals 0. Okay, so remember A. Okay, what was the assumption? Let me show you the assumption one more time about division algorithm. A is an integer. I have no assumption about A. I'm not assuming A is positive or negative. A could be any integer, whether positive or 0 or negative. B is positive. So my assumption is that B is positive integer, but A could be any integer. So, but I can still consider different possibilities for A. So one possibility is that A is bigger than or equal to 0. In that case, if I set M equals 0, then what do I get? Then A minus BM is going to be A minus 0 is going to be A, which is bigger than or equal to 0. So in that case, A would belong to S, and therefore S would be non-empty. M here can be any integer. Now, one of the integers, 0 is one of the integers. So if you consider 0, A minus 0 becomes A. And my assumption in case 1 is that A is bigger than or equal to 0. Therefore, a minus bm for m equals 0 in this case is a, which is a number bigger than or equal to 0. Therefore, it is in S, right? Because S was all integers of the form a minus bm, where a minus bm is bigger than or equal to 0. Well, one such number is a minus b times 0. Why? Because a minus b times 0 is a, which is bigger than or equal to 0. According to the assumption of case 1, I don't know whether a is bigger than or equal to 0, but in case 1, because I'm considering different cases, in case 1, proof by cases means in each case we consider one possibility. So one possibility is that a is bigger than or equal to 0. Right now, I'm just considering that possibility. What about other possibilities? We'll do it in the next case. In case 1, I'm assuming a is bigger than or equal to 0. So a minus 0 becomes a, which is bigger than or equal to 0. Therefore, this number a belongs to S, and therefore S is non-empty because it has an element. Now, what about case 2? What is the other possibility about a? If a is less than 0, then how can I show that a is non-empty in this case? The previous argument does not work anymore, because if I set m equals 0, then a minus 0 becomes a, which is less than 0 in case 2, in the assumption of case 2. And I cannot say a belongs to S anymore in this case, because elements of S must be bigger than or equal to 0. Look at these elements of S are elements of this form, which are bigger than or equal to 0 by the definition of S, by the requirement that we put in definition of S. So previous argument does not work here, but I'm going to use m equals a in this case. So set m equals a. So previous case I set m equals 0. In this case, I want to set m equals a. What do I get? Then a minus bm becomes a minus ba. And this means a times 1 minus b, right? And this is bigger than or equal to 0, right? Why? Because why a times 1 minus b is bigger than or equal to 0? What do I know about a? I know that a is negative, right? So a is negative, because a is negative. And what about 1 minus b? 1 minus b is going to be also less than or equal to 0. Recall, b is a positive integer. One minus a positive integer is less than or equal to 0, right? And a is less than 0. So if I multiply two numbers where one of them is less than 0, one of them less than or equal to 0, the result becomes bigger than or equal to 0. So in this case, a minus ba would belong to S. And again, that means S is non-empty. So we showed, what did we show? We showed that S is a non-empty subset of N. So that means S has a least or contains a least element. Call this element contains a least element, let me say, of the form a minus bq, which we will denote by R. Every element of S is of the form A minus BM. One of these elements is the least element. So M here could be any integer. But for one specific value of M, this number becomes the least element of S. That value of M, I'm going to call it Q. And this Q is the Q that we are looking for. Right, look at the definition of S again. A minus BM, M belongs to S. So M could be any number here. For one of these values of M, this number A minus BM becomes the least element of S. That value of M, I'm going to call it Q, which is the Q that I'm going to show that is the Q that we're looking for. So that's why I said least element is an element of the form A minus BQ, because every element of S is of the form A minus BM. Instead of M, I'm just calling it Q, which is the value that leads to the least element of the value of M that leads to the least element of S. And this expression A minus BQ, I'm going to denote it by R. And this R again is the remainder that we are looking for. I'm going to show this, okay? So how did we find, remember we were looking for existence of Q and R, but we consider a set S is of the form A minus BM. M could be anything in this set, but one of the values of M is the value that leads to the least element for S. That value of M, I'm going to call it Q. Then I get A minus BQ, which is the least element of S. This expression, this whole expression A minus BQ, I'm going to call it R, which is the R that I was looking for. And that's what I'm going to show you in a few seconds. Okay, so what can we say? So we can say R equals A minus BQ, i.e. A equals BQ plus R, right? And what else do I know about R? And R is bigger than equal to 0, right? Why? Because every element of S is bigger than equal to 0, right? S was elements of the form this, A minus BM, where these values are bigger than equal to 0. So every element of S is bigger than equal to 0. R is one of them. Therefore, R is bigger than equal to 0. So I have A equals BQ plus R, and I have R bigger than equal to 0. Am I done, do you think? I was looking to show existence of numbers Q and R, where A is equal to BQ plus R, and R is bigger than equal to 0, less than B. So that's the only thing that is not done yet. So I also need to show that R is less than B. So it is left to show that R is less than B, because we have A equals BQ plus R, which is what we needed. We have R bigger than equal to 0, which is what we needed. We also need R less than B. Again, please look at the statement one more time. Here, A equals, look at this statement, A equals BQ plus R, we have it. R bigger than equal to 0, we have it. And less than B, we still need to prove this part. Okay, so how can I show that R is less than B? I'm going to use proof by contradiction to prove R less than B. We use proof by contradiction. So suppose R is bigger than equal to B. Then consider, let me call it R2 equals R minus B, which is going to be bigger than or equal to 0, first of all, right? Because my assumption is R bigger than or equal to B, so R minus B bigger than or equal to 0. Also, R2 equals R minus B is going to be what? What was R? R was A minus BQ. So A minus BQ minus B, right? See, R was A minus BQ. So R minus B is A minus BQ minus B. If I simplify this, this is A minus B times Q plus 1. And hence, R2 belongs to S. So why can I say R2 belongs to S? S, again, let me remind you, S, what was S? S was all elements of the form A minus BM, where this number M comes from the set of integers, and the whole expression A minus BM must be bigger than or equal to 0. Now let's look at R2. R2, first of all, is of the form A minus BM. It's A minus B times Q plus 1. Now, so my M here is Q plus 1, and Q plus 1 is an integer. And is also non-negative. R2 is non-negative. Any number which is of the form A minus BM and is non-negative, according to the definition of S, belongs to S. So I can say R2 belongs to S. And this is a contradiction. Why is the contradiction? Why is this a contradiction? R2 belongs to S is a contradiction because R was supposed to be the least element of S. See? Here I said S contains the least element of the form this, which will denote by R. So R was supposed to be the least or the smallest element of S. But look at R2. R2 is R minus B is less than R. So how is that possible that R is the least element of S, the smallest element of S, but some element less than R also belongs to S? That's not possible. If R is the least element of S, nothing less than R is allowed to belong to S. Okay, so contradiction with R being the least element of S. Okay, note R2 is R minus B, so that means R2 is less than R. Okay, so we reached a contradiction, and therefore, so this contradiction shows what? So this shows that R is less than B. The contradiction was here. We want to show R less than B. Then we use proof by contradiction. We assume R is bigger than or equal to B. We reached a contradiction, which means R has to be less than B. So we showed the other parts were already done, right? So A equals BQ plus R with R bigger than or equal to 0, less than B. Okay, so this is the proof of division algorithm. And of course, we did some examples as well for division algorithm.